Hey guys, so while I was recording, let me back up. The first part of this video, the first like hour or so, well, the first half hour is me fucking around with my audio settings and rambling about shit as usual. Then the next like half hour is me going through Euclid's argument for Book 1, Prop 8. And then I was trying to figure out in that argument I didn't use GeoGebra at all because it's one of these construct an impossible situation and prove it's impossible. It's kind of hard to do that with GeoGebra. And then I decided to record myself making a thumbnail because that seemed like an interesting video. And while I was doing that, I came up with a better argument than what Euclid has. Or I don't know if it's a better argument, but Euclid's argument is a proof by contradiction. So he says, let me describe an impossible situation and then prove that it's impossible, which is, I don't know how I feel about, I mean, proof by contradiction in general can be useful. However, constructive arguments are better. And so what I found is, I don't know if it's a proof, but I found sort of a demonstration using constructions of the basic idea. So the basic idea is the side-side congruence theorem. So we have three sides, so I've labeled them blue, red, and green here. Let me actually take you through this diagram. And then over here, and so the vertices, I used RGB logic with the vertices. So blue plus green in RGB logic is cyan. So that's the cyan vertex. Blue plus red in RGB logic is magenta, and then red plus green in RGB logic is yellow. And then so I said, okay, so the blue, I'm going to call that the base, and these other two are the sides. It's arbitrary, but... So the first thing I'm going to do is I'm going to use our procedure for copying line segments from the beginning, and copy this blue line segment over here. And it doesn't actually matter. Oh, shit. So I think the basic point is the pink. I don't know. No, I think I don't know. Okay. So yeah, pink is the base point in the construction. Okay. So we copied this line segment over here. And then so I copy. How's this work? Yeah, okay. So see how this circle has a center at pink and has a radius of blue. I don't know if you can see that. This circle has a center which is pink and a radius which is blue. And I copied that circle over here to the center at pink and the radius of blue. And then I copied the red circle centered at pink to a red circle centered at pink. Okay? Then copy a green circle centered at cyan. See this? Green circle centered at cyan to a green circle centered at cyan. And then I thought the better version of the argument from last time was you look at the intersections of these two circles and say there's only two intersections. And I guess Euclid didn't like that argument for whatever reason, but I think this is more technically correct. Anyway, the point is that if you have the side, yeah, so anyway, this is a constructive argument showing, hey, we have two sides here, side, side, and side. Side, side, and side. Oh, he wanted to establish that the angles were equal. Right. And he does this with this very nebulous... Okay. Now I'm less convinced that this is a better argument. See, there isn't much in his postulates to correctly deal with angles. And again, this is kind of why this is, I think, the weakest spot in all of Euclid's reasoning is this concept of angle, so far at least, because it's not really well defined at all. He uses a bunch of unstated properties of magnitudes. There's a bit of waffling right at the beginning. And I think with rational trigonometry, it's a lot, you can really pin down exactly what things are. Anyway, I've talked enough. So what I'm going to do is this is going to go at the beginning of the video. Then we're going to have the normal video that I plan to release, and then the video of me making this thumbnail. I'm going to have to edit text later, add text. Me making the thumbnail, that's going to be the last 45 minutes of the video. All right. I will see you in the I'll see you. God damn it. How do I zoom out? Okay. I'll see you. I don't know. Whatever. The founder loves you. Keep listening. Bye. Hello. My name is Dr. A.J. Coomer, PhD. I am the smartest mathematician who has ever lived. We're reading Euclid's Elements. I think this is book 1, proposition 8. I have not even looked at it even a little bit. So there's a link to this website down in the description. And so the way it's organized, so I think what I link to is this page. Okay, this is just some dude's website, but it's very, very good. And so up here in this little circle, you can click 1. So we're reading book 1. There's 13 books. So there's a lot to go over. And my goal was to do one of these a day, and then I kept skipping days, and then I skipped like 30 days in a row. So I did get a new microphone, so now I feel like playing with my new toy. Not sure how much I like it. I mean, so the old microphone was a Shure MV5, which the sound quality on it was excellent. It did not get along well with Leonard at all. This one is a Rode pod mic, but it's not just the microphone. I had to buy a microphone stand. Then I had to buy an audio interface. I don't recommend this microphone, by the way. I think I will keep it. The thing is, the problem is here. Let me just show you in OBS. So I have this microphone like literally like 2 inches from my face. Okay. And I'm going to show you here. Let me zoom in for you. I didn't check the other video to see if the zoom in feature worked. Like it works on my monitor. I don't know if OBS is capturing it though. We'll have to see. But anyway, you can see the waveform. This is right next to my face. Right next to my face. And we can open the filters. Okay, the only filters I have, I turned off the gain filter. Let me zoom in even more. I turned off the noise filter. I have a limiter because, with no gain, right next to my face, literally like an inch from my face, and I have the gain knob on the USB audio interface turned all the way up. This is just barely loud enough. I do have a compressor, but even if I turn that, let me turn off all the filters, okay? Here, the only thing, okay, by the way, and the stand did come with a pop filter. You hear that? Pop, pop, pop. It has a very bad built-in pop filter. Pop. Sorry, headphone users. Anyway, I'm going to turn the compressor and the limiter back on because the stand came with a pop filter, but it sucks because it doesn't. I bought a cheap stand and a nice stand because the nice stand takes like 3 weeks to arrive. Anyway, so I don't have any gain on. It's nice because it doesn't have any noise, but it's I don't know. So the point is, I guess need a. Okay, so the problem is I've spent $300 for basically no upgrade in my audio. I do like the stand; it does look cool, but I think I'm gonna need to buy a bunch more audio shit so that it's loud enough, or that I can have it a foot away from my face and then you can still hear me. So now if I turn the gain up, so now it's like a foot away from my face. Let me gain it up to like 10 decibels. So the last one I recorded, the audio interface hadn't arrived yet, and so I was just using an XLR to USB adapter. So now this is like a foot away from, it's a foot away from my face. And I was just using an XLR to USB adapter, and I had to gain that up like 20 decibels and have a noise filter, and so the audio was... You know, here's the thing. By the way, don't ever learn about microphones. It is one of the worst things you can ever do. Oh, this is actually... I don't know. Should I leave it up here? I think I'm going to turn the gain off, because I think, well, what do you guys think? Oh, you guys aren't live because this is recording, and it'll probably take me like a month to upload this. I'm going to turn the gain back on, but I'm going to turn it. I'm going to do like, I think 10 decibels is maybe too much. So let's try 7.5. God damn it. 7 point. I was also having issues with OBS crashing, and I upgraded OBS, and that seems to have fixed things. How is the noise? Let me shut up for a minute. Oh, it's not bad at all. Okay, I don't have a noise filter going. Okay. Anyway, so I guess for $99, this is kind of what you expect. The MV5 had objectively better audio. I don't know. Maybe the thing is I don't know. Don't learn about microphones, especially, like, here's the thing. Not a single person has complained about my audio, partially just because nobody watches my videos, but you know what I find out? I find out that there's like weird, like there's a company, this is a rumor I've heard from somebody who works at the company, where they have like a chat room where of people who follow my shit. And so I never hear from these. I hear from one person who works at the company, and that's it. But I have 30 it's just, anyway. Nobody follows me. Nobody likes math. Nobody likes Greek geometry. But I like math, and I'm more important than you. So, anyway, let's talk about some math. So, what does it say? Is this what we just did? Proposition 8? Because this... Oh, Christ. This is going to be another one of these things where we construct an impossible situation and then have to prove that it's impossible. Great. Lovely. All right. It's 1 p.m. I can start drinking. Anyway, if two triangles have the two sides equal to the two sides respectively, and also have the base equal to the base, then they also here. Let me, in case this works here. If two triangles have the two sides equal to the two sides respectively. Okay, so this is the side congruence theorem. So this is what I thought the other theorem was. But I think the other theorem, the thing we did yesterday, I don't remember, implies the side congruence theorem, because you can do the thing where you... Yeah, okay. I think you can... Yeah, it's just going to be 1.7. But again, the proof is going to be some obfuscated bullshit where you construct an impossible situation and then prove that it's impossible, so it's going to be impossible to visualize. So, anyway. Let ABC and DEF be two triangles having the two sides AB and AC equal DE and DF respectively. Okay, namely, yeah, AB equal to DE and AC equal to DF. That's what respectively means. And let them have the base BC equal to EF. I say that the angle BAC also equals the angle EDF. If the triangle ABC is applied to the triangle DEF, and if the point B is based on the point E, the triangle ABC is applied? What does that mean? Superimposed, maybe? Yeah, so this is a thing where he has this like very nebulous notion of what equality means. So I think what he means. So we would say in modern terminology that there's a would we say a similarity transformation? We would say, so the way that you would do it today is you would say that there is a group of transformations of the plane. Let me explain what this means. Grab the drawing pad. Okay. Which one of these is the drawing software? Here we are. I switched to KDE. Fuck off. And then it does weird things, like see how the colors are all dampened? Here, let me zoom in. See how the colors are all fucked up? Okay, so what I have to do, there's a lot of weird little behavior like this. So I minimize the window and then bring it up again. And now the colors are fine. So anyway, so the way that this would work today, and obviously this idea didn't exist in Euclid's time. So, and okay, this is bothering me that it's not here. Okay. So in today's terminology, you specify a group of transformations. Okay, group is a reserved term. In transformation, this just means function. Okay, so what is a group? Let me tell you about what this is. If you watch my abstract algebra series, which I'm going to get back to, because I was kind of being a pussy-ass bitch about copyright, because I was worried that what I was doing didn't count as fair use, but I've learned more about fair use, and it's unambiguously fair use, because the most important thing is that I am creating a different product that doesn't compete with the original product. And also, I'm constantly telling, like literally every video, I would say, here's a link to go buy the book down below. Go buy the book. All right. Anyway, so group of transformations. So what is a group? Okay. So a group, this is a set. Again, you're defining one piece of jargon in terms of another jargon. So set means unordered collection. So that doesn't keep track of repeats. Okay, so maybe a way to think about this would be, actually, I think a better way to do this, which I'm not going to go into right now, I will get into this probably in my Math for Programmers playlist. I'm probably just going to redo that because I don't know, because one of the videos was like 2 hours long and nobody's going to watch that. Anyway, I think a better way to do this is to talk about signed multisets, because that's actually a simpler structure. And then sets are, this is the simpler structure. This is the fundamental structure. Okay, and so and then a set is a signed multiset mon 2. Okay, so a signed multiset is one way to think about it. I'm going to assume you know what a function is, okay? Let me talk about a signed multiset. You know what? I'm not going to, well, okay. Signed multiset would be a collection of objects that keeps track of multiplicity, but the multiplicities could also be negative. So let me give you an example of a signed multiset. I'm going to actually use Lisp notation. Okay, SMS for signed multiset 0, 0. Actually, I'm not going to use integers because that's going to be confusing. Heart, it doesn't matter what goes in here. Heart and triangle, okay? And the idea is that if I ask what is, let's set this equal to x. Why is my hand just sweaty? My drawing pad is damp. Okay, and so if I ask the multiplicity, what is the multiplicity of heart in x? This would be equal to 2. And then the multiplicity of triangle in x would be equal to 1, okay? But I could also have these multiplicities be negative, and then, the multiplicity of something that isn't in the set. So multiplicity of, I don't know, taco. How do I draw a taco? The multiplicity of a taco in x is equal to 0. So something that's not in the set is equal to 0. And then, so all of the natural operations of addition, subtraction, multiplication, the empty set, these are actually a very natural data structure to deal with objects. And so, like in Erlang, the way that you do this, so in Erlang, I've coded these. So you would do type, I can't remember exactly the syntax, type smx of x. You code this as a map, from x to an integer. Okay, now, if you take every one of these multiplicities and you reduce it mod 2, then every element in the set occurs either 0 times or 1 time. Okay, that is called a set, a signed multiset where all of the multiplicities are done mod 2. So let me show you an example. So I'm just gonna use S. I'm gonna put S and then a bracket for a signed multiset. 1, 2, 3. Okay, plus the signed multiset. Ooh, how about plus or minus? Plus or minus. That's dumb. You know what? I'm going to use S expression notation because that's really clear. Okay. And I'm going to switch to white because I'm tired of blue. Okay. So let's let x equal to the signed multiset of 1, 2, 3. Okay? And we're going to ask, what is x plus x? This is going to be equal to the signed multiset. And by the way, x is also equal to the signed multiset 3, 2, 1. It doesn't, the order does not matter, the multiplicity matters. That's the idea of that's what multiset means. It's a set that keeps track of multiplicity. A set ordinarily does not keep track of multiplicity. Anyway, a signed multiset of 1, 1, 2, 2, and 3, 3, let's say. Or maybe the way we'll code this is signed multiset of, and then we can use Erlang's hash notation. There we go. 1. Can't remember, how does this print? I'm just going to print it like this. 1 goes to 2, 2 goes to 2, and 3 goes to 2. Okay. If we take so this is plus. In sets, you have instead something called the union. I think a more fundamental operation is something that in set theory is called the symmetric difference. So, or the XOR. So the plus let's call it plus mod 2 of x, and x is equal to, well, each one of these has multiplicity 2, so when we reduce it mod 2, we're going to get the empty set. So we reduce all of the, we do exactly the multiset arithmetic, but mod 2. And you can recover all of the operations using plus, and then to get the intersection would be times mod 2 equals the intersection. So multiplication mod 2 is equal to the intersection. So SMS mod 2 operations plus is the symmetric difference, and then set operations. And let me draw a Venn diagram. I'm going to be talking about this in my Math for Programmers playlist. Venn diagram. So if we have A, let's call this A, and let's call this B. In signed multiset logic, it's everything that's not the intersection. Okay. Times would be the intersection, which you usually denote with a cap, and that is everything in the middle here. Okay. Then we can get the union, so I think it is, okay, here you can, there's actually an easy way to do this. So the union, or the inclusive OR, what we do is we take, we write, can do this, 0, 1, so this is a Boolean representing if it's an A, and this is a Boolean representing if it's in B. I just redo the truth table each time. If you've seen the WFC playlist, this should be familiar. It's Math After Dark. What the hell is it called? It's on, I don't think it's on the Odyssey channel yet. The Rumble, there's a link down below to the Rumble podcast channel. And it's called, you know what, I'll just try to remember to link to it. It's called Sika 2. So it's the podcast I do with Craig Cannon, and it's the second one we did where I explained this to him too. I'll try to remember to link that below. 0, 0, so 0, right, 1, okay, so, right, it's 1 plus A. See, you can just do algebra with these. So the union is this, which is equal to 1 plus A plus B plus AB, and because 1 plus 1 is equal to 0 mod 2, this is equal to A plus B plus AB. Okay, this is the expression in signed multiset mod 2 that gives you the union. So A plus B is AB. And then, so this is the union. Let me actually, A plus B plus AB. So these are products. So A times B, that's a product. A plus B plus AB. This is the union in set theory, which is this. Okay. And then, so the CIA's math is all based on set theory, which I think is wrong because, like, I mean, just the sign multiset abstraction is just clearly a superior abstraction. The union is everything, and then you can get the complement. The complement, to do that in sign multiset logic, you just add 1 plus A. This is the complement. So, and for this, so you have A, and then you have like the universe out here, and it's everything that's not in A. Okay. But I think there's in sign multiset, we have this like very clean, literally just mod 2 algebra applies in sign multisets. Anyway, I told you I was going to tell you about a group of transformations. Okay. So a set is a signed multiset mod 2. Signed multiset, I think this is I haven't given you a formal definition. I wrote some code somewhere to go over the signed multiset logic. It's really simple. You can probably figure out exactly how it works. So addition, subtraction, multiplication. You can't do division because it's integers. I wonder if you could do division. There's probably a way to do division by mirroring like quotienting, but I'd have to think about that. Anyway, so now you know what a set is. Okay. So what a group is. So a group is a set. So we have a set. Let's just call the set G. Okay. And there's a binary operation. So there's some operation, let's call it Q, which takes G, this is a Cartesian product, G times G. So all pairs, a Cartesian product just means ordered pairs. So tuples, G times G to G. So it's a function that takes ordered pairs of elements in G to G. So an example of a group operation, so the integers are a group, and they're a group with respect to addition. That's an example. Okay. So first thing is there must exist an element E in the group such that Q of E with X is equal to Q of X with E, which is equal to X for all X. So in the integers with addition, this is 0. 0, it's the identity. So identity. Okay. The group law must be associative. So Q of X, Q of Y, Z must equal Q of X, Y, Z. So it has to be associative. There's one other thing. Every element has to have an inverse. So for all X, so this is saying addition is associative. For all X in G, there must exist Y in G such that Q of X, Y is equal to Q of Y, X, which is equal to E. So with the integers in addition, this is saying that that every element has an additive inverse. So for instance, 3 plus minus 3 is equal to 0. So it's saying, and god damn it, it feels like there's another rule. Okay, I'm gonna have to look this up because I'm not confident. Let me look this up. This is embarrassing, but I feel like there's another rule, but I can't. Okay, definition. Associativity, identity, element, invert. No, that's the 3 definitions. Okay, so what this is saying is that there's so if we're talking about a group of transformations, typically the groups you talk about are transformations, and this Q function is function composition. So you could think of 3 as a transformation on the integers that adds 3 to every number. So 3 is the element. 3 is really, lambda x plus x3. That's what 3 means. Okay? God damn it. Lambda x plus x3. Okay. So this is the typical way you think about a group. You think about it as a group of transformations, and then your Q function is just normal function composition. So normal function composition is associative. There's an identity function, and the interesting part about a group is every function is invertible. Let me give you an example of a group. Would be rotations. So you fix an origin in the plane, Okay, all rotations that fix the origin in the CIA's world, this is all matrices. What is it? Cosine theta, sine theta, minus sine theta, and cosine theta. I might have that backwards. So this represents a counterclockwise. If you take a point x, y, and you multiply it by this matrix, it will represent the rotation of the output of this will be the rotation of the point x, y counterclockwise and there's a rational version of this, but I don't feel like getting into that right now. Because what you do is you use the fact that you can get a rational parameterization of the circle pretty easily. I'll link to a thing where I explained that to Craig, and then you can just cook up a matrix by using the fact that all complex numbers are just matrices. Okay. There's a way to get this rationally. I just don't feel like going into it right now because I just know this off the top of my head. I don't know the rational version off the top of my head. So this is a rotation of x, so xy counterclockwise by an angle theta. Okay. So if, let's say this is x, y. Okay. And then let's call this matrix M. Okay, and let's say our theta this is our theta. Okay, this would be M times X, Y. So all rotations that fix the origin, obviously each rotation, there's an inverse rotation. The rotations are going to be associative. In these cases, they're also going to be commutative. Those are a group. Now, this is actually like the most common pattern you see in pure mathematics and upper level mathematics is you take a space that's very familiar, and then what you do is you pick a group of transformations and you say, I am going to pretend that any two elements that differ by one of the elements so in this case, what we would do is we would take our plane and we would say, okay, any 2 points that differ by a rotation, we're going to pretend they're the same point. Okay, so I probably didn't draw these with the same magnitude, but let's just pretend I did. Okay, that's close enough. And so what we would get is sort of our structure would be the structure on circles, because what it's saying is any 2 points that are on the same circle, those are exactly the points that are going to differ by a rotation. And so we go from the plane to the set, from the set of points to, from this we would get the set of circles. Okay, so the way that we would talk about congruent, so the entire, let's just pull up. Okay, so the point I was trying to introduce you to there, and I've talked about this a bit in my abstract algebra playlist. I talked about quotient. There's one video, it's called like the most fundamental idea in math or something like that. I think I called it the real fundamental theorem of algebra. Something like that. And I had a really obnoxious thumbnail. Anyway, the idea is that this is the most common way that we talk about equality now, is we talk about our normal equivalents of triangles, which would be, say, A, B, and C is equal to D, E, and F. So the points are the same. The vertices are the same. Let's say we consider the data of the triangle to be the vertices. But then what we do is we would define a group of transformations. So what our transformations would be, the Euclidean group of the Euclidean symmetry group, let's say, the Euclidean symmetry group. So group theory So I want you to think, typically elements of a group, by the way, of a group, these are called symmetries. So symmetries means we pretend, symmetry means essentially the same. Okay, so the Euclidean symmetries, these would be translations. This means moving. So if we have a triangle over here and it goes, we have the same triangle over here, then those are the same triangle. It doesn't matter where it is. Rotation. So this segment is equal to this segment because they're the same length. Well, pretend they're the same length. They're probably not exactly the same length. And then there's another one, which is reflection. So let me give a really extreme example. So this is a very oblong looking triangle, and this is the same triangle as this one. Actually, let me pick a better example, because that one is, this is equal to this triangle. There's no way to rotate this triangle to get to this one, or there's no combination of translations and rotations. So each one of these is obviously invertible. You can invert a translation. You can obviously invert a rotation. Each reflection would be its own inverse. So you do the same reflection twice, you get an inverse. You compose two different reflections, you get a rotation. Rotations, by the way, these are the 2x2 matrices with a determinant equal to 1. These are 2x2 matrices with a determinant equal to -1, I believe. Something like that. Anyway, so you combine translations, rotations, and reflections. That, I believe, is the complete set of Euclidean symmetries. Okay, and so the way that we would talk about this today, the whole point, my whole diversion, which, how long have I been talking? I've probably been talking an hour. Yeah, 37 minutes, and we haven't even talked about the math. But anyway, the point I was making with that was that is sort of the way that we talk about, how's my volume, by the way? That is the way that we talk about God damn it. Anyway, that would be the way that we would. Euclid. My point is that Euclid has this very vague and nebulous notion about equality, and today the way we would make that a lot more concrete is, well, we talk about points being equal if they have the same coordinates, and then we would say, let's say a triangle would be defined by its vertices, or a circle would be defined by its center and radius, whatever. And then what we would say is that if we can apply one of these symmetries to get from triangle A to triangle B, then we say they're the same triangle. So this is really the most fundamental construction idea in all of mathematics, is this idea of quotienting by a group. So you divide a space by a group. That's the idea. An example that you're familiar with in everyday arithmetic. So let me just, oh, God damn it. Where did I put the paint program? Okay. Let me just give you one example that you're already familiar with. Z, this is the integers. This is a group. Okay. Another group is all multiples of 12. So this is, 0, plus or minus 12, plus or minus 24, plus or minus 36, etc. Okay? If we take z and we say, I don't care about differences by multiples of 12, okay, you take the normal arithmetic on the integers and you say, I don't care about differences by multiples of 12, you get clock arithmetic. So here you get things like 11 plus 2, well, that's equal to 13, but you use 3 equals, by the way, when you're doing modular arithmetic. So 11 plus 12 is equal to 13, but mod 12, that's equal to 1, which is also equal to, say, minus 11 mod 2. Or mod 12, sorry. So you're already familiar with this idea from clock arithmetic. And I was showing you z mod 2z. That was the mod 2 thing I was talking about above. So anyway, you're already actually probably a little bit familiar with this idea because you do modular arithmetic every single day when you think about how time works. Anyway, so that's an example of when you use the idea of quotienting by a group. In this case, we would be taking a group and quotienting. Well, because multiplication actually has a more sophisticated structure than just the group. You're taking actually a ring and quotienting by an ideal, but forgetting about that. Anyway, if two triangles, because a group only has one operation, a ring has two operations, and then I can't remember. My abstract algebra is really weak. That was why I did that abstract algebra playlist, but I'm gonna start doing that again. Don't you love my focus? So what have we talked about? We talked about my audio settings in OBS. We talked about planar groups of isometries. I told you about data structure that you have never used, which is a sign multiset. We're 41 minutes in, still haven't talked about the math, and my coffee is cold. Thanks. 1 second. All right. So this is the side congruence theorem. That's what this is. So there's a bunch of different congruences of triangles. So meaning if you know that this is x is equal to y, a is equal to b, and p is equal to q, then you can conclude that the two triangles are equal. So what this is saying is that if you have all three sides of a triangle being equal, then there's no way to construct two triangles that have the same sides, and the order might matter. It probably doesn't because there happen to be three sides, but maybe if you had a more complicated figure, the order would matter. I think with three, I'm not sure. Anyway, but the way Euclid is going to prove this, I bet, is by doing the thing where he says, I'm going to construct this impossible situation and then prove it's impossible, and we're not going to be able to visualize it. So if two triangles have the two sides equal to the two sides respectively and also have the base equal to the base and also have the angles equal, which are contained by the what? Then they also have the angles equal, which are contained by the equals straight lines. So, okay, we have our two triangles. Okay, we say that BAC is equal to EDF. If the triangle ABC is applied, so applied I think would mean, in modern terminology, take one of the groups of transformations that would transform ABC into DEF. And if the point B is placed on the point E and the straight line BC on EF, and then the point C also coincides with F because BC equals EF, right? Then BC coinciding with EF, therefore BA and AC. BA and AC also coincide with ED and DF. For if the base BC coincides with the base EF, the sides BA and AC do not. Oh, and the sides BA and AC do not coincide with ED and DF, but fall beside them as EG and GF, then given two straight lines constructed, right? There will have been so we're using the theorem from yesterday, which was this. So here, let me open the GeoGebra file. So I think the better way to see this, so the way that it was constructed was really confusing to me. Let me make these. Okay, here's what I'm going to do. The points are fine. I'm going to make these a little bit thick. I'm going to make them all thicker, and then that way it should be easier to see. I'm just going to make everything as thick as possible. So this is pretty much the same theorem that we were doing yesterday, because I thought that that was the side angle side congruence, because I was like, well, yeah, and I'm going to turn off these angles because it's just confusing. I don't think the angles are really that interesting. That's not the interesting part of this. All right, and then I'm going to make these a little bit darker so they're easier to see. Okay. Okay. So we started with AB. Okay. And this D is irrelevant. Okay. For now. Okay, so we have the triangle. We start with the triangle ABC, and I'm going to turn off the grid. How do I turn off the grid? There we go. So we start with, let me make this bigger. And we'll zoom in. Okay. So we start with the triangle ABC, okay? And what I've done is I've constructed, let me make this even clearer to illustrate where these object property, I'm getting nauseated. Let's make this green. That's a very ugly green. How about, why are all of these green? Okay, I'm getting nauseated. Okay. That green. Okay, so the green circle goes with the green. Okay, there we go. So the green circle goes with green, the purple circle goes with purple, and that was the idea. Okay, so again, the theorem yesterday was like, we're constructing one of these impossible situations and then showing it's impossible. So what the idea was, and I think Euclid's proof was actually technically wrong, but he didn't have, the modern correct way to do this would be to use algebra, some algebraic geometry to show that, you know, to count the number of ways two circles can intersect, but oh well. So originally we have the triangle ABC. Okay, and I'm going to hide D, J, and this. Okay. So originally we just start with these triangles. Okay. Now what he was saying was that if you have a side emanating from B and a side emanating from A that are the same lengths, then what was it? Then they must intersect at C or, okay, it was very confusing. Let's fix ourselves to being only on one side of A, because you see there's this other intersection down here. What the point is that everything that is equal to the purple segment, every segment that is equal, meaning it's the same length as the purple segment that emanates from A, has its other endpoint on the purple circle, right? Has its other endpoint on the purple circle. And everything that emanates from B that is equal to the green segment has its other endpoint on the green circle. If we fix ourselves to one side of A, then there is only one point at which these two circles intersect. Okay? So I was thinking that this was the side-side-side congruence theorem. And the reason we have to specify on one side of A is because on the other side of A, we have this. Of course, he doesn't define what on one side of A means. In our modern terminology with determinants and signed areas, we can do that. Go look at my abstract algebra playlist. I talked about the determinant and the signed area and all that. I'm going to get back into my abstract algebra playlist. That was I enjoyed that, and I've been more depressed since I haven't been doing that. Anyway, so up here, there's only one point at which these two circles intersect, and Euclid, of course, had some weird proof that was not technically correct, where he was, again, constructing some impossible situation. So what he was doing was constructing a third point D and showing that it was impossible by trying to derive a contradiction, but I think his proof wasn't technically correct. So by constructing this new triangle and showing that, you know, some logic of angles was broken, but I didn't understand his proof. And I don't think angles are a very good abstraction. I think spreads and I think determinants, using determinants, linear algebraic metrics, inner products, that's the correct way to think about trigonometry and geometry, and you don't need angles at all to do it. Go watch Wildberger's rational trigonometry videos because he explained it well, and I'm gonna get into that, and I'm gonna explain it. I think because it's Wildberger's original work, so I think I can probably actually explain it a little bit more clearly than he can, because he's, you know, for him it's decades of work, and for me I only understand the simple version, so maybe I can explain the simple version a little bit more clearly than he can. I don't know. Anyway. Okay. So this is the, we got to go back to the next one. Here we are. Okay. So what he's going to be using that theorem that I just explained, which was, okay, so we take ABC, we move it to EDF, and we have AB equal to DE and AC equal to DF. Then by that theorem that we just had, which is we make this circle from E to D, so we draw this little circle here, and from F to D, we draw that little circle there. If we restrict ourselves to one side, by the way, the way that you would define side with respect to the signed area is you would fix a vertex order, and then if the signed area of the triangle is positive, then that's one orientation, and if the signed area is negative, that's another orientation. And that's how you define orientation, actually, is by signed area. Anyway, so actually, you know what I'm going to do? I'm going to make this full screen and zoom in. There we go. That's better. Okay, then BC, right. So what he's saying is, put this triangle on this triangle, and then because of the side equalities, they have to be coincident. This point A has to be on D, and that's the only other way. So this is a bunch of word salad to say that A has to be on D, and therefore, right, again, his logic here is, let's assume that this is not the case, and we're going to use the previous theorem to say that's impossible. I don't like the way that, but again, 300 BC, whatever. Therefore, it is not possible that if the base BC is applied to the base EF, the sides BA and AC do not, so therefore it is not possible that if the base BC is applied to the base BF, so applied, I guess in Euclid's verbiage, means take the group of transformations that would take, in modern terminology, take the groups of transformations that moves BC to EF. Therefore, it is not possible that if the base BC is applied to the base EF, it is not, the sides BA and AC do not coincide with ED and DF. Therefore, they coincide, so that because that the angle BAC coincides with the angle EDF and equals it. Therefore, if the true triangles have the two sides equal to the two sides respectively and also have the base equal to the base, then they also have the angles equal, which are contained by the equal straight lines. So this is the side-side-side congruence theorem for triangles. And his logic is, take this side, put it over here, and because there's, you're going to get into trouble if the orientation is reversed. That's what I'm confused by. Because according to this way that he has set this up, according to the way that he has set this up, these two triangles are not congruent because there's no, or that these two triangles are not equal. So the order matters a lot. Anyway, right, okay. And his thing is using the previous theorem. That's his logic. Okay, the side-side-side congruence theorem is the second of Euclid's 3 congruence theorems for triangles. See the note on congruence theorems after proposition 1.26. Let's open that in a new tab. As in the proof of 1.4, this proof employs the hazy method of superposition. I believe that he mentions the phrase group of transformations in the notes down here. Congruent. Let me look for the word group. Yeah, so whatever the intended meaning of superposition may be, there are no postulates to allow any conclusions based on superposition. One possibility is to add postulates based on a group of transformations of space, or if restricted to plane geometry, on a group of transformations of the plane. That's what I was just saying. Charles Dodgson or Lewis Carroll would have said, that guy's a fun, go read about him, would have said that using group theory is not appropriate to an elementary exposition of Euclidean geometry. Heath has described a more elementary conservative basis on the commentary in his commentary on this proposition. I gotta get to Hilbert's Foundation of Geometry. See, the problem is that an angle, you can't actually make sense of the concept of angle. So I like Wildberger's approach. And in my Math for Programmers playlist, or maybe in my Abstract Algebra playlist, I'm not sure, I'm going to get into this. I don't know. I think I'm going to make the Abstract Algebra playlist just reading Artin. I don't know. I should quit trying to make things so structured, because the structure is strangling me. Use of proposition 8. So this proposition is used in a few of the propositions in book 1, starting with the next one. It is also used several times in the books 2, 4, 6, and no, that's not 6, that's 11 and 13. As in 1.4, the two triangles need not lie on one plane. Propositions such as 9.4 in book 9 apply as this theorem. Okay, as in 1.4, the two triangles need not lie on one plane. Oh, right. Okay. Propositions such as 9.4 in book 9 apply this theorem to the case when the two triangles are not coplanar. Okay. It's side-side-side congruence, but you have this problem, which is by this construction, two triangles with different, that are congruent but have different orientations. Yeah, rational trigonometry is better than this. But I mean, you can't blame Euclid. I mean, this is the foundational. You need to understand. This is the foundational text of mathematics as a formal discipline, and like any discovery. So I'm we have this idea that geniuses just sort of magically come up with these ideas out of thin air, and occasionally that does happen. Usually the way discovery happens, just stretching. I've been here for an hour. How long have I been talking? An hour. Okay. Usually the way discoveries actually happen is, what they do is they take insights that have been present in the zeitgeist for a couple generations, for maybe a century or two, and they boil it all down into a really, really simple formulation. Newton, okay, maybe let me use a modern example, which is cryptocurrency. So the idea of a distributed ledger had been around before Satoshi. Git is very similar to Bitcoin in that respect. Git is just a distributed ledger. Git is actually much closer to being distributed. Bitcoin's not distributed, but I'm not going to get into Bitcoin. Bitcoin's stupid. It's not stupid, but you know what I mean. No, you don't. Bitcoin. Okay, I'm not going to talk about Bitcoin. But anyway, the idea of a distributed ledger had been present before, but what the killer application of it was, hey, you can use this to solve this other problem, which is how do we solve the double spending problem? The way banks do it is by just charging overdraft fees. That's the way banks solve it. Is they don't solve it, they just punish you if you. So they punish it with an incentive structure. The way that Bitcoin solved it was with a pretty fancy cryptography scheme. And that was sort of the killer app there. And so what Newton did, the idea of calculus, the idea of taking derivatives that had been around hazily, even the Chinese had figured out several centuries before Newton, they had figured out things like the Pascal triangle, which some Chinese mathematicians had figured out. And the elementary ideas of calculus can be found in the Pascal triangle. And so, but we attribute calculus to Newton and Leibniz because what they did, well, Newton especially, Newton figures out that, hey, Kepler has these rules for the motion of the planets. For instance, that the orbit of a planet is an ellipse and the sun is one of the foci of the ellipse, blah, blah, blah. And so what Newton does is he figures out that actually here's this very simple abstraction called a force, and here's how gravity behaves as a force. And I can use, from my laws, I can prove that my laws and this calculus, I don't think he used calculus for this. I haven't read his exposition. But he said, I can prove that my laws imply Kepler's laws. So my laws are more fundamental. And my laws also basically enable you to do all of physics. All of basic mechanical physics are just Newton's laws. And it's incredible. And so, I mean, Newton's one of the greatest he's probably, he's obviously, he's Newton. He's one of the greatest geniuses to ever walk the face of the earth. But the way discoveries work, it's not, I don't even remember why I was talking about this, but the way discoveries work, it's not somebody has a flash of insight and suddenly comes up with all sorts of new shit. What it is all of the ideas are sort of exist in this sort of disarray out in the world, and it's one person who comes along and figures out an abstraction that cleanly handles all of these weird ideas that seem related, but nobody can quite figure out how. And typically the way they do that is by demonstrating with a killer application. And with Newton, it was proving that his laws implied Kepler's laws. With Bitcoin, it was showing that, hey, you can use this distributed ledger idea to do currency. And then, anyway, I've talked long enough. So thank you for watching if you watched all the way to the end. I'll see you in the next video. Founder loves you. Bye-bye. Hello, I'm Dr. A.J. Coomer, Ph.D. I am the smartest mathematician who ever lived. So I was watching the video I just made, which is Euclid Elements Book 1, Prop 8. And I was trying to think about, it's better if there's a thumbnail, so I'm not going to upload it for a little while. Because you know what I might do is I might add this video into the end. It was pretty long, so. But I like if there's a thumbnail that kind of illustrates what the theorem is. So, and the reason I'm not going to upload it is because I want them up in sequence, and Rumble takes forever to monetize the video, and then what happens is they monetize them just sort of in a random order, and so I want them uploaded in sequence. And so the rest of you are all, if you're watching on YouTube. By the way, if you are watching this on, well, you're not because I just said that. Yeah, fuck it. Only like, I don't know. Okay, by time, like 40% of my content is up there on YouTube, because in terms of time, the vast majority of my content is podcasts, because those are minimum like an hour long, and there's tons of those. Those are up on the Rumble and BitChute channels, and then there's an Odyssey channel, and I'm not very good. I haven't finished uploading everything over to the Odyssey channel, partially because I wanted to remaster the first episode. Anyway, what was I going to say? Oh, I was trying to think about a thumbnail, and I thought of a cool thumbnail idea, which was use our segment copying procedure, and then do the segment copying procedure twice to, yeah, do the compass copying procedure twice. So, but I don't quite remember what the procedure is, so I'm going to try to reverse engineer it live, and so this is going to be a fun test. All right, first thing, I don't want the grid, and I don't want axes. Okay, so the first thing we start with, I remember, is a segment. Okay, and then I'm definitely going to need colors. I'm going to need a lot of colors, so let me just go ahead and open the object properties. And style. I want this very thick. Okay. And then I'm going to make my segment. Okay. Now what I want to do is copy this segment over to like down here somewhere. So how do we do that? So how do we... Okay, let's make a point down here. Okay. And how does this work? The copying the compass procedure, I don't quite remember. Okay, so we have this circle, and I want to get this circle over here. And what was the way you do that? I know what you do is you make a really big equilateral triangle. And I'm going to move this out of here so that it's just obviously not part of the picture. Okay, and how do we do that? Do I want to cheat or do I want to try to remember it? I think it was the second one. Maybe do I have the thumbnail saved? Let me look and see. Okay, that was I remember how to do the equilateral triangle, but where can I remember? Okay, let's just look. How to duplicate a compass. Right, okay, so so we have to make a circle over here. Oh wow, this looks cooler in the black. I don't know. Okay. Okay, I'm going to hide these for a moment. And so I think what we want to do, so let's do our equilateral triangle procedure. Okay, that's right. And okay, I'm going to have to cheat again. Do our equilateral triangle procedure. Ah, okay, I see. Okay. Okay, so here's what we're going to do. I'm going to pick the... God damn it. Okay. Okay. You see, what we got to do is we pick this point down here. Right, okay. So let's construct this point over here. Okay. Then what we do, let's make our... I don't think we quite need our equilateral triangle, do we? No, yeah, that's right. We need lines. I don't think we need to construct this segment over here. I think that's completely extraneous. Yeah, it looks completely extraneous. Line, okay. We need this. Okay, and then we need this point here. Okay, and then we're also going to need this line. And what we're going to do, we're going to also make a circle from here through here. Then, sorry, there's a lot of points, but now I see what we're going to do. And now we have this segment here. Okay. So what I can do, I can move this really far away. Okay. And there's a lot of circles here. Okay, and so this is what I said, we're going to need some colors. So this color, let's make it pink. This also needs to be pink. Let's make this like light gray. Slightly darker. There we go. Okay, this will need to be like, we do like a blue, just to illustrate that which things are sort of paired up. Okay, and this will be a red, red. This will be oh no, that's more of a pink. Okay. So now what I can do, okay, now let's make these visible. Again, I'm just great at, okay. Now what we're going to do, we're going to make a new segment. Over here. Style. So what I'm going to do is I'm going to copy this side over here. Okay, we've done that. This side, okay, I might run out of colors, oh well. I think what, okay, we're gonna need to be more limited in our color choices. So that was blue. This will be a darker blue. Does that work? Yeah, that's a nice. This can be a really light blue. Okay, and this will be like a powerful blue. Okay. Now this segment, this will be our red segment. So a powerful dark red. Style, make it very thick. All right, so we want to copy that over here. So we need A to correspond to D. Okay, so let's try to remember again. Nope. Circle with the center through the point. Nope. What? And then we need these two circles. Nope. The other two circles. Why does GeoGebra decide that, let's just fuck with AJ today? That'd be fun. Okay. So this gets the color of like a very light red. This gets the color of like a slightly light. Okay. Right, and then so these lines. Right, we need, oh, we have the same join again, don't we? Oh, do we even need these circles? No, we don't. No, okay, so these, okay, that's interesting. We don't need these circles. Anyway. Oh, that's right. We do need. Okay, what we do need. Right, we do need this point right here. Nope. The intersection right there. Okay, so where are these two lines? That's a conic. Let's make these like gray to. There we go. That's much harder to visualize, isn't it? I liked the old way better. I've lost the colors. No. There we go. All right. These should be like a... No. Why am I fucking around with the colors? It doesn't matter. Anyway, what does matter is that we construct this circle and that this new GeoGebra, I am not in the mood. That this circle is red. Okay, and that therefore there we go. Okay. Now what we can do okay. This is where it gets interesting. Okay. So this I'm actually going to make See, this is, I think, a stronger version of Euclid's argument, actually. Because what I'm doing is I'm saying, okay, so I'm going to try to copy this triangle over to here. So I copy this segment, and now I'm going to copy this segment. Okay. And I'm going to make these kind of dark. Okay, to emphasize this. And make them bright, but maybe make them thicker. And this, how about let's make this one thinner. Okay, so this is going to be our green segment. Okay, and basic color, this has to be like a green. Can we do like a pink? No, that's too close to red. All right. All right. Well, green's ugly is the problem. All right, I'll live with green. Okay, and then style. One thing I'm going to do is I'm going to move this point way over here. Okay. All right, so we need to copy green over to H. Okay. So what is our procedure for doing that? All right, so we're going to start with this, and let's make this light green. All right, that's kind of ugly, but we'll deal with it. Then we also are going to need... Yeah, we need to make our equilateral triangle. That's right. Whoa. Why do these coincide down here? Is that just... do they actually coincide over there? Or... I don't see any reason why they should. Let me move H around. Yeah, okay, that looked like that was just a coincidence. Okay, so these two, let me move H in over here, because then it's a little bit more clear. Okay. Okay, no, these need to be darker because otherwise I can't see what's going on. Okay, so we're copying B over to H. Okay, I gotta hide this other shit. No, we definitely need this. Okay, we don't need the original segment. We don't need point A. And what is E? So, okay, that's a point. We don't need I. Okay. We do need... Right, we're copying... Now I'm getting confused. Yeah, we're copying this over to H. Okay. Right, so now we're going to pick one of these points, so I'm going to just pick this one. Intersection. Okay. Now these lines, these are... Yeah, take these two... Right. Okay. This is, I think, a much better version of Euclid's argument. Because... Okay. Let's make this... Okay. Circle... Oh, shit. Okay, there we go. And we're copying this over to H, right? Let me just double check. Just all these fucking conics. I can't see. Okay. I'm getting lost. Okay, right. So what we want, okay, I actually do want to go back a little bit because I think in my undo haste, I deleted a seg. Oh, right. Okay, this is the point. Okay, so this is the point, which is what matters is this circle, and I haven't made a segment yet. And what we're going to do is we're going to construct a green circle as well at H, and that those two circles only have two intersections. Okay, right. Okay, so where are we in our H construction? I am going to go back and undo. Most of this. Nope. Okay, this conic getting drunk sick again. Okay, getting motion sickness. Okay, this I'm going to label as green. Okay, I'm also going to label this point as green, even though the point isn't really green. I'm just emphasizing which color each thing goes with. Okay, what is J? Okay, J is a red point. I'm just going to label it red. Okay, even if it's not really red. And I, I'm guessing, is also red. Yeah, I looks like an important red point. S, I think these were the duplicate conics that we made. Right. And then Q, okay. Okay, where's I? Okay, our points should be like bright pink. Maybe our vertices. So A, let's make this bright pink, just so that we agree. And C, okay. D, H, because these are sort of fundamental specialized points here. So the argument that we're going to end up making is we're going to see this red circle right here, the DJ red circle, okay? we're going to construct a very similar looking circle. Yeah, okay, I can already see it. Okay. But just so that we're getting less confused, okay. You see this point right here? We're going to start with H and go right to okay, and again this M, god damn it. This M, make it green. This will make green, doesn't matter. Okay, and then style. Okay, these need to be de-emphasized. So these get to be like a lighter green. Does that work? So the point is now there's only two triangles we can construct over here. Okay, and is there a way for me to just turn off all of the labeling? Because that would be nice. Because now there's so much. Okay, so this is intrinsically a red. And let's make this very red. Yeah, let's do that. Let's make this very green. Emphasize that this is, because that's really what's important. Color very, very red, and this should be very red. And this N is a fundamental point. Okay, and this P over here, this is actually very fundamental, isn't it? Basic color, and it should be, if we're going to match things up. Okay, and then okay, these labels are annoying me. Show label. Show label. Is there a way to like, yeah, don't show any labels. There we go. Okay. Where is E? Okay, this really does deserve to be... This deserves to be like blue. This deserves to be like a purplish. That weird unholy purple. Okay. Okay, and the point is this down here is going to be pink because it's another fundamental point, or it's a vertex. Show label. Okay, and what we got, I want to go through and de-emphasize, because this is actually a much better argument than what Euclid has done, which, god damn it. Really? GeoGebra, why are you like this? GeoGebra is like designed to just be maximally annoying because it never does the thing that is reasonable. Okay? Anyway, these two segments right, okay. So, there's too much noise in this. Okay. Let's make these... Is that... Oh, okay. That's right. So these I'm just going to delete. Okay, and these... You know what, maybe we should make these pink? I don't know, man. And then this point down here, we should make it... All right, so... Okay, this transparency is killing me. Okay, it's this. I'm going to have an opacity of 100%. Oh, that's what we should do, is play with the line style. That could work. because there's just too much noise going on here. But I think this is a better argument than Euclid's argument. So let's take this and make the line style dashed. Okay, and let's make it a 9. Okay. Let's make it 11, and we'll make it dashed. This, once again, we'll make 11, and we'll make it dashed. 11, and we'll make it dashed. This, again, dashed. How's this? It is like a beautiful symphony of nonsense. And you think the Greeks would have... This is a cleaner argument, in my opinion, than what Euclid did. All right, so... And I'm glad I chose to do that. Okay, so this is Euclid Elements, Book 1, Prop 8, Better Proof. .ggb. Okay. Or I don't know if it's a better proof. It's a cleaner argument that I think illustrates the point better, which is that there's only two, that if you do this segment copying and this segment copying, there's only two possible triangles to construct. Yeah, I don't know. Sort of undecided. So let me blow this up. Yeah, I think this is something where... Okay, let me... God damn it. I don't want labels. New labels. No labels. All right. How do we like this? I think what we want to show is that this doesn't depend on orientation. So we're going to go over here with it, just so that it's obvious. And should we color code these points? I think we should. So the blue-green intersection, object properties, that's what we want. Okay, this blue-green intersection, let's make this, color should this point be? Purple? No. Yellow? Yeah, let's make that yellow. Because blue plus green in RGB logic is yellow. Okay. Red plus green in RGB. Is it... No, blue plus... What is red plus green? This is bothering me. Okay, so yellow. Yellow is red plus green. Okay. What is blue plus green? So red plus green is yellow, so these should be yellow. The red-green intersection should be yellow. Okay. What is blue plus green in RGB logic? So red plus blue is magenta, so we'll keep these two as magenta. What is red plus green? That's going to bother me. Cyan. Okay. So these are cyan. I didn't know that. They look like, that just looks like bright blue to me. All right. Uh-oh, where our colors don't match. Green plus blue. No, these are meant to be yellow. So these are... This is meant to be cyan, because our blue goes from magenta to cyan. Okay, so I think this has been going... Okay. So what should I do? I think what I'll do is I'll add a thing at the beginning of the video saying, hey guys, I went through Euclid's argument, and then while I was making the thumbnail, I thought of a cleaner argument. I don't know if this is a cleaner argument, but it is a... it certainly is an argument that I think it doesn't rely... It's a construction-based argument rather than sort of a more Baroque contradiction argument. Anyway, I don't know. Again, I don't like any of these arguments as much as just a straightforward rational argument. But anyway, this video is getting too long, so I'm going to stop recording. And then, well, you know what I'm going to do is I'm going to stop recording, and then I'm going to go back and record the beginning of it.